So welcome guys to a whole new series, and in this series we'll analyze WannaCry malware sample. So as I've already showed you guys, we've already set up secure virtual environments to analyze our samples. If you haven't checked the videos on how to set up Remnux and Flare virtual machine, you can check the links in my description. And I also introduced you guys to the malware analysis lab for our first analysis of Emotet malware. So by now you should have some basic skills on analyzing malware samples in static and dynamic analysis phases. We've already checked a couple of tools and we've utilized some of the tools to analyze our previous sample. So for this sample, we'll analyze two variants of WannaCry ransomware. We have the first version of WannaCry, which is WannaCry 1.0. And this was the first version, and it has a SHA-256 value of this figure, and we're going to obtain a malware sample from VirusShare. So I'm also going to attach the links to VirusShare if you want to download some of the samples. And for the second sample is WannaCry version 6.0. We have the SHA-256 value. This one was a much later version than the original version, which is 1.0. So if you have VirusShare, you can access some of these samples. If you don't have an account from VirusShare, you can request their team. Then they'll email you and give you access to VirusShare so that you can download some of the samples. So in order to download the first sample, you can just copy the SHA-256 value. I'll attach everything, including the details of the malware samples and the links on my description so that you can also download. So I already have a VirusShare account. So what you do is you can just paste the SHA-256 value. And as you can see, we have our first variant over here. So we have some exit data, which is the file metadata. And we'll check more of this in our static analysis phase. So we'll expose some of these details once we start analyzing a sample. So primarily, we're going to analyze these two versions, and they are both ransomwares. So for those guys who don't know what ransomware is a malicious software that utilizes encryption techniques to lock the victim's files, and it will demand a ransom payment for the release of the locked files. And in typical cases, once a ransomware infects a machine, then it modifies the file extension, and the file is unreadable, and in most cases it's usually encrypted. So for WannaCry, it emerged in 2017, and it caused a significant disruption, especially in various industries. The ideal industries that WannaCry tried to target was mainly government institutions and healthcare facilities, because these facilities normally handle sensitive data. So the hackers designed a ransomware that could encrypt most of the sensitive data files, and they demanded ransom payment in the form of Bitcoin. As you can see in a picture over here, they utilized the blockchain network for its anonymity and for its security. And for different variants, we have different Bitcoin addresses, and we'll come to that and analyze some of the Bitcoin addresses that these ransomwares demanded. In most cases, WannaCry is designed to exploit a vulnerability in the Microsoft Windows operating system, and it primarily exploits the SMB protocol, which is the server message block, and it will spread through the network. So once one machine is infected and it exploits the SMB, then it can propagate over the network. So the attack mainly utilizes a double pulsar tool, which was developed by the National Security Agency to create backdoors in Windows operating system and facilitate the installation of the WannaCry code. So despite the availability of preventive measures that were deployed by most of these organizations, most of the businesses were caught off guard by this exploit, and this emphasizes that businesses need to deploy effective security detection measures, and they need to update some of these measures from time to time because some of these exploits normally change. So in our case, we'll analyze both samples in our virtual machines, and as I showed you guys before, if you want to download the sample, you can download it from virus share. We have the details over here, and you can just simply click the download button and it will download your sample. So in our virtual machine, I have both samples downloaded, and to extract the sample, we'll have to extract the zip. So Flare virtual machine has an inbuilt zip extractor called 7zip, which we'll use to extract the files. So we have our two variants downloaded over here, and they are denoted by their MD5 hash values, and we'll extract both of them. The password to the sample is infected. For most malware samples that come from virus share, the password is infected. So we have our first variant extracted. We extract the second one using the same password. So just to show you guys, the password is infected. So before we do anything, the first rule of thumb that we normally do in our analysis is we'll check the sample hash value on VirusTotal just to confirm if the sample was previously submitted. So we'll begin with our first variant. Our first variant, which is the first version of WannaCry, WannaCry 1.0, has this specific SHA-256 value. So we'll search it on VirusTotal, and I had already conducted a previous search, and you can see the sample is already submitted, and it's detected by 64 out of 70 security vendors. So most of these security vendors already have this specific virus signature in their database. So some of the details, the MD5 value, just to confirm, the same as our sample over here. So we have the history, the creation time, this variant, first submission, which is 2017. We have some of the names that are given to this specific variant. We have disk part, super key, and we'll see some of this information once we start our static analysis phase. Some of the imports, we have kernel 32, user 32, ADV API. You can see some of the relations, including the domains it will try to contact. Maybe we'll see some of this in our Wireshark traffic. Remember, we already have Remnux running, and it's simulating some of our network traffic. So be sure to capture these in our dynamic analysis phase. Then proceed to search the second variant. So in order to search it, go to VirusTotal, click on search, then paste the file hash. So for the second variant, which is WannaCry 6.0, it is denoted by this SHA-256 value. as you can see, this variant is also submitted, and like the previous one, this one is detected by around 67 security vendors. Some of the details about this variant, as you can see, we have the MD5 hash value. Just to cross-check, we compare our MD5 value for the second variant. And as you can see, they are both similar. We have the history, the creation time, some of the names. We'll check more of these details in our analysis phase. So we've confirmed that both samples are already submitted on VirusTotal, and we already have some hints and clues about some of the names, domains, and other details about the variant. So to begin our analysis, we'll start analyzing our first variant. So this was the original variant denoted by the SHA-256 value ED01 and so forth. So what we typically do, in this case, I'll try and analyze the file header and check the basic properties of this file. So we'll check some of the starting header values from HexEditor and confirm the nature of this file. So we'll open HexEditor. Then we'll open our first variant. Just click on File, then click on Open. Then we'll access our first malware sample. So right from the start, you can see that there is a presence of a magic MZ key, the sample, which can classify this specific sample as a portable executable. So in most cases, if you see the magic MZ value in the first 2 bytes of the offset hex values, then this confirms that this is a process executable. Then for the other step, if you notice the first 2 bytes, the offset values begin with 4D and 5A. This also confirms that this is a process executable. And as you can see, we already have our first hint that this is a process executable. So we'll also analyze this sample on PEStudio to check some of its properties, including the resources, the libraries, and some of the basic structures of this file. So in order to run PEStudio, go and search for PEStudio. Then you can just drag and drop your malware sample. Then as you can see, we already have our first 32 bytes. And the first 2 bytes, as you can see, is 4D5A, which you already saw on HexEditor. It starts with MZ. We have the file type. This one already gives the category of the file, which is a process executable. We have the size, which is 3114 through 68 bytes. The version of the file. Then we have the file description, which is disk part. And from what we've seen on VirusTotal, we have some of the names that were given to this file, and one of the name is disk part. So we have our first hint from PEStudio. Then the file signature that it uses is a Microsoft linker. The date of compilation, which is November 20th, 2010. And if we check the history timestamps from virus total, then we can see the creation time, which also matches the compilation time. So we have the stamps over there. The name of the file, which is disk part. We typically see different names for these files as an obfuscation technique used by threat actors to try and hide some of the details about this file. Further examination of the variant on PEStudio will begin by checking some of the resources. And the flagged resource is a PKZIP signature, which suggests that this variant is using compression and zipping techniques. If we check the libraries, we can see there's a library segment, and there's a couple of libraries that are built in within this variant, and this variant tries to access. So as you can see, the library segment, the executable, exposes a chain of essential libraries that are linked to the Windows runtime. So we can see kernel 32, user 32, ADV API 32, Msvcrt. So kernel 32 basically provides core functionality like memory management, creation of processes, and also creation of system file operations. So if we see this inclusion, it might suggest that the malware is trying to engage in low-level system interactions. For the user 32, it offers a variety of user interface services. So in this particular scenario, it might enable the malware to interact with Windows, dialog boxes, and user inputs. And from what we'll see in our dynamic analysis phase, we'll see some of the dialog boxes that this variant displays once the system is infected with this ransomware. So for the ADV API 32, so this one provides access to advanced system services, including the registry, and in particular cases, trying to modify the registry keys, authentication, and also other security functions. So in this case, you might determine that the malware is trying to modify some of the registry keys. And as you saw before from our analysis in the Emotet variant, if you haven't seen the video, you can check it. The link is on the description. We've seen that Emotet also modifies some of the registry keys to maintain persistence and also to modify some of the system calls. Then we have the Msvcrt, which contains functions that are related to the Microsoft Visual C++ runtime library. So in this case, it might support applications that are running on C and C++. So in the inclusion of this specific library confirms that the malware is developed using a Visual C++ programming language, or it relies on a specific C and C++ runtime functions. We'll head over to the import section and you can see some of the imports. So we'll jump to the import section so that we can see some of the imports, and the ones that we'll specifically analyze are the ones that are flagged. So we have 114 imports and 16 flagged imports. So for the first import, we have write file, which suggests that this variant might try to create a file and write some data into it. Set file attributes, as explained by the name, create attributes based on the file. So it might depend on the specific file that it creates. It will create the specific attributes that are associated with the file. create directory. So in this case, if it wants to create a new folder directory in a different location, it has the capabilities to do that. It has the capabilities of copying a file. So in this case, if the ransomware is designed to create with a C2 beacon and communicate with it, then it might try to copy a file that is downloaded from the back door. We have create a process, and from this we've already seen in the libraries that we analyze, this variant tries and accesses the kernel 32, and like we said, the kernel 32 library gives access to process creation and system calls. So since it has the libraries to access this system's function, then it might create a process, and this might be a malicious process, and we'll examine some of the processes that are created from this variant in our dynamic analysis phase, where we'll check all the processes using process monitor. So as well, create a service. We've already seen some of the libraries that are associated with these system functions. Start a service. We have registry key creation, and we've seen that other variants also modify some of the registry keys to maintain persistence and other functionalities. And yeah, so these are some of the flagged imports that are within this specific variant. We'll switch back to the version so that we can see the file version name and its description. So we've already checked the offset values, and we already know this is a process executable. The language is English US. So it's signed as a Microsoft Corporation program. So in most cases, if you see malicious programs signed with official company names, then this can be an obfuscation technique, or a technique where this malware variant tries to hide and encrypt some of its content using a legitimate program. The file description, we've already seen in our virus tutorial, such that this file has other different names, and this part is one of them, and it's called a Dissection executable. And for the product name and version, it's also signed using Microsoft for hiding and obfuscation techniques. So we'll switch back to another different tool that we'll use for static analysis phase. And for this tool, it's called CFF Explorer. And as you can see, it displays the basic file properties, including the name, the file type, which we've already determined from analyzing some of its headers, that it's a process executable 32-bit. For the file information, you can see it's using Microsoft Visual C++. We have the file size, creation dates, modification dates, and access dates. We have the MD5 values and the SHA-1 values. And like we've seen before, this file is signed as a Microsoft Windows application, and this is an obfuscation technique that we've already talked before, that threat actors normally use to deploy programs as legitimate programs. So we'll check some of the imports like we've seen before, and we have some of the libraries that are within this specific variant. We talked about some of these libraries, and we've seen all the imports that are called by these specific libraries, and some of the imports that were flagged on PEStudio. We've checked the resources as well from PEStudio, and dependency worker is also an inbuilt module within CFF Explorer. And the dependency worker displays some of the libraries that we've already seen. So these are some of the libraries, and talked about these libraries. HexEditor, we've already seen the first offset values and their corresponding ANSI code, which is MZ. And from this, we determine that this variant is a process executable. So for the packers, if this variant is using any UPX packer, then we can unpack it. But in our case, we don't know which packing technique that this variant is using. And in order to know that, we'll use a separate tool called exeinfo. And as you can see, this is the visual output of exeinfo. And what we'll do is copy our variant and drag it into exeinfo. So as you can see, it's using a Microsoft Visual C++ signature. From here, we have details of the file size displayed in X values and other details as well. So if we scan some of the signatures, you can see the details about some of the signatures and the versions of the signature and the inbuilt Microsoft compilation code version. So it's Microsoft Visual C++ version 5.0. So if you check the PE header, we can see the machine type that this variant is designed to infiltrate, and it's targeting the Intel i386 architecture Windows. For the operating system version, Windows 4.0 and T. If you check the version info, we've already seen some of the details, and we already know that this variant has a file description of disk part, and it's disguised as a disk part executable and signed as an official Microsoft Windows application. So we'll proceed to extract the strings from this variant using the strings tool, and we'll pass all the strings to a txt file called edstrings.txt. Then we'll check the contents of the txt file using Notepad. So if you check the txt file, you can see some of the imports that we detected on PEStudio, and we've seen some of the flagged imports that are used by this specific variant. We have a couple of libraries and new libraries that are detected. We can see the WannaCry file, and from the software lists, we can see a target list of all the file extensions that are targeted with this variant. So this is the list of all the file extensions that are targeted in a system. In most cases, once the file is infected, then the extension is changed. There are also unique signatures over here. So you can see WannaCry signature, And this can be a distinctive marker that this specific variant that we are analyzing is WannaCry ransomware. We have the other libraries like kernel 32. We have the encryption algorithms that I use. So this is RSA and AES encryption. So the sample we have over here is a binary file. And what we'll do is we'll rename this file to an executable and check some of the contents that are inside. So we'll just rename it and add an exe extension. So right now we've added an extension to an executable. Remember, we've already analyzed the headers, and from the details that we've gotten, we know that this is a process executable. So in order to check the contents, we'll use 7-zip and we'll say open archive. And as you can see, we have some other files over here like b.wnry, task.dll, executable, and a task.sc executable. So we already know from the PKZIP signature that we extracted and we got it from PEStudio that this file is using a compression technique. And we've changed the extension to an executable and checked the file contents within 7-zip. And we've seen that we have other files that are hidden inside this executable. So the next step will be to analyze this specific file using IDA. Then we'll select the other file, which we've renamed and added an exe extension. And remember, this is a portable executable. So we'll leave the settings to default and we'll click OK. So we'll start by checking some of the imports that are made with this variant. So from IDA, if you want to check the imports, click import section. And from kernel 32, we can see a couple of suspicious imports like create a file. We have write a file. And we also have set file pointer. So in these cases, if you see such suspicious imports, then most likely the malware is trying to open, modify, and overwrite files. And in ransomware cases, this is heavily used in overwriting original files with encrypted versions of the file. So we have other suspicious imports like get computer name, get the current directory. So if the ransomware wants to traverse across different directories, then can use this specific import to know the location of the current directory. Create processes. If it's trying to create suspicious processes, then it might do that as well. It might also terminate a process. So let's say if it loads a malicious process and it wants to hide some of the footprints, then it can terminate the process. So these are imports from the different libraries that we denoted. Same case with the ADV API 32. It has the options to create and modify any new registry keys and also start any system services. So we also have srand and rand. And in most cases, srand represents the seed for the pseudo-random number generator, and it sets the starting point for the sequence of numbers that rand will generate. And for rand, it will generate pseudo-random numbers, and it produces integers that are based on the seed from srun. So in most cases in malware, it's often used to generate file names, folder names, and even parts of the encryption keys. If you notice these specific ransomware using RAND instead of strong APIs, then it means that the key generation might be predictable and potentially reversible. So we've seen some of the suspicious imports, and we've seen most of them from PEStudio. But IDA also gives you an overview of the imports that are made from the specific libraries. And we've seen some of the suspicious imports. Generally, most of these imports are suspicious. So let's begin by analyzing our first import, which is a set current directory A import. So just double click on it, and you will utilize a feature called XREFs. So XREFs is a function which stands for cross-reference. It's an inbuilt feature within IDA Pro, and essentially it will reference all the places in the program code where the specific import is called, used, referenced, or jumped to. So in our case, if we want to check other sections of the code segment where this specific import is called, we'll utilize the XREFs feature within IDA Pro. So click on Next on your keyboard, then we'll check this call. And what you'll notice with this specific code segment is that there is a couple of suspicious strings. So we have a suspicious string over here. And if you remember, guys, from our variant on PEStudio, we noticed that this specific variant is using a PKZIP signature for compression techniques. And some of the files that are zipped might be password encrypted. So this may be our first hint in unzipping some of the code segments that are using the PKZIP signature. So yeah, if we check the assembly code, in this scenario, we're using the IDA view segment, which gives the assembly code of the program. So we have the LEA, EAX, and the file name. So in this section, it will load the address of a string variable that contains a file path into the EAX. Then for the section of the call segment of this code, so we'll check the set current directory A call. So it will call this specific function, and this will change the current working directory of the process. So if it was working in a different process, then it will change and allocate the specified directory that this specific variant tries to access. Then if we scroll down, we can see some of the strings that are used. So remember, we said this string might be useful in using the password encryption techniques to try and unzip some of the PKZIP signatures that are built in within this specific variant. If we scroll down, we have the attribute +h. So this is a command line execution code, if you see. And in most cases, it will make all the files in the current directory hidden. So this might be an obfuscation technique that is used by this variant. And by executing this specific command, it will make all the files hidden and not accessible to the end user. So this is already a red flag, and we have a string over here. And if we scroll down, we have icalcs and /grant everyone the directory letter headers F, T, C, and Q. So in this case, this command grants full permission to all users recursively. And this also makes the file writable so that the ransomware can encrypt the files within that specified directory without any permission issues. Then we have the delays. So in our case, the delay is in milliseconds. So every time it executes a command, we have a delay of milliseconds. So in this case, it's DW milliseconds. And for this delay, this code pushes the delay before and after the commands that are executed, so that it can ensure all the commands are executed before any other command segment is reached. So from this command sample and from this code segment, we can infer that the variant tries to change the working directory of the target folder. It sets the file attributes to hidden to make the changes less visible to the user. It modifies some of the user permissions to ensure that the encryption is possible on all the files within the specified directory. And we also have an unknown string mentioned over here, which might be used as part of the mutex during this infection phase. So let's continue and analyze our second import, which is the set file attribute. So just double click, then you use the xrefs option, and we'll check the second call. So from this call, we have two important Windows APIs over here. We have the get file attributes W, and we have the set file attributes W. So for the get file attribute W, to retrieve attributes of a file or a directory, for example, if the file is hidden, or if it's a system directory, if the file attribute is set to read only, it will still extract some of the attributes from that. And in this case, this variant might most likely try to use this current state of a file before it tries and modifies anything before it adds the attribute. So it will check for the files within a specified directory, review all the attributes within that specific file. Then for the set file attribute, which is the other Windows API call, will allocate new file attributes to this specific variant. And if you notice, we're using attribute H, or in this case, it's labeled as ORAL6. So in this case, the attribute is set to 6. And if the attribute is set to 6, this means that the file attribute is hidden. And it will most likely mark the file as hidden in the system, which is obviously used as an obfuscation technique to try and hide some of the file attributes within the infected files. So just a bit of context, the get file attributes retrieves the current attributes of the file. So once it gets the attributes of the file, it will allocate new attributes using the bitwise OR. So in this case, the attribute is set to 6. And in most cases, for the bitwise OR, the file will be set to attribute hidden, and also the file will be set to attribute system in the address 0x02 and 0x04. So it sets the hidden and system file bits in the attribute value before modifying the existing attributes that are returned from the get file attributes. So it doesn't necessarily replace them, but it tries and hides some of the file attributes. So in this case, the malware or this variant is most likely using this specific feature as an obfuscation technique. And this block of code is about hiding the files at operating system level. And it's one of the first stealth moves that most of the malwares normally make before doing most of the damage on the system. So for this section, we'll check the section of the code in the program where the program is writing data into a file. And what we did is we went to the right file, import module that is within the kernel 32 library. And we use the same feature xrefs, and we checked the second call. So this is the second call, and from this code segment, in the first section over here, what the variant is actually doing is it's checking some of the preliminary checks, and in most cases it will compare the values of the EDI against a specific constant, and in our case this is a specific constant that is given, and in most cases it could be an error code or it could be a special flag value, and if these conditions are met, then data will be written into the file. So it's a conditional preliminary check, and if all the checks satisfy the condition calls within this specific segment, then it will write data into the file. So for the next section, EBP, the number of bytes written. So in this section, it will prepare a pointer to store how many bytes that are actually written. Then it will use the push instructions over here. So remember we said in either view, this is assembly code. And in this case, it's using push instructions to point specific variables to store the bytes that are written. Then it will execute a call called write file, which allows the Windows API to write data from the memory into the file on the specific disk that is infected. Then we have the error exceptional handling. So for the error exceptional handling, we have the test EAX. So after data is written into the file, EAX contains the return value. So if it's a non-zero, then the data written into the file was a success. If it's zero, then there was an error during the data writing, so it resulted to a failure. So if the write failed, then the program proceeds to the error handling section over here in test. So after that, we have the loop flow control over here, and it checks whether a certain byte in the stored source data is zero, and it will also go through the data chunks that are within this code segment. And from what we've seen over here, this snippet is very likely a part of a file encryption of payload drop routine, and it will handle files using the file handler EBP plus H file. Then the buffer pointer will point the data to where it's written to, and it will also be used to encrypt some of the content. So remember, ransomwares usually encrypt file content, change file extensions, and they require cryptographic keys or any other keys to decrypt some of the content. So this is a workflow on this specific segment on how this variant writes data into files and how it normally encrypts. So let's switch to ADV API 32 library. From the import section, we can see reg create key. And if you remember from our previous analysis of Emotet malware variant, the variant created and modified registry keys, maintain persistence, and also modify some of the system calls. So we're also seeing something similar to Emotet, and this variant is also trying to modify and create some of the registry keys. So we'll check this specific key, and from this key we can see the import is a reg create key. We'll check the second call, and like I said before, the reg create key creates or opens a registry key, and it's a common persistent mechanism that is used by malware to maintain persistence. So, for example, if a malware variant tries to modify the registry keys in run, at startup, or in current version, then it's most likely trying to enable persistence and also execute on startup. Then we have another directory import. So it's get current directory, and I think we've already talked about this. So for this code segment, it will fetch the current working directory into the buffer. So it fetches the current directory, it sets it in the buffer, then it will use the red set value. So it creates a key, gets the current directory information, inserts it in the buffer, then it will get the registry value. And once it gets the registry value from the registry handle reg create key, so remember it creates a registry key, then it will set specific values to that specific registry key. So the EDI section over here, the assembly code, holds the value name of the registry key. So in most cases, these cannot be assumed as a random registry writing, but as a persistent mechanism that is used by malware variants to modify specific registry keys. So in most cases, the malware does this even when you try and restart the system, especially if the startup registry key is modified, so that the malicious program can execute automatically even when the system is booted. We have another suspicious import over here called delete critical section. So this is an API that cleans up any critical section of an object, which is typically used in thread synchronization. And in most malware variants, these critical sections are often used to prevent multiple threads from running and also synchronize the encryption and decryption process. And in some cases, it will ensure that one instance of an action runs at a specified times. So it prevents multiple instances from executing at the same time and ensures only one instance runs at a time. So we typically see this in malware after it's finished the operation, acquired the synchronization, and encrypted most of the files that are within that system. And it's a multi-threaded process. So the encryption phase, the modification of the registry keys is a multi-threaded process. And for this section, it ensures that the malware is trying to coordinate most of the internal threads, ensuring only one instance runs at a specified time. We have another import over here, which is find resource. In this case, you can see finds a resource, loads a resource, logs a resource, and gets the size of a resource. So for the find resource section, we look inside the executable for a resource within the given name, LP name, and also the type XIA. So in this case, XIA is a resource type. So the offset type is denoted by XIA, and 080AH assembly code over here is given as the LP name or the resource name /ID. So malware often hides payloads inside the resource section, and as you can see over here, this specific variant is trying to exploit some of the resources section within the system. So once it locates the specific resource type that is denoted over here with the resource name, this one, it will load a resource. So in this case, it will load that specific resource into the memory. Then once it loads the resource, it will log the resource. And right here, we're talking about this specific variant getting a pointer to the actual bytes of the resource so that it can be read and executed. So once the variant gets the actual bytes, it will determine the size of the resource. So it will retrieve the size of the resource in bytes so that the malware can know how much data it can write into that specific resource. So it's a very classic technique that is used by malware to embed secondary payloads within the main binary file so that they are not immediately visible as separate files. So it's like an obfuscation technique or a propagation technique that the malware uses to hide any secondary files. And after loading and locking the resources, the malware can drop some of these executables into the disk, inject some of the memory into another process, and it can also use it as a data or encryption key for the configuration data. So we can determine that the malware is pulling a hidden resource from inside its own executable. The resource type is XIA, and it finds it by name and by type. So once it finds the resource by name and by type, it will load it into the memory, get the size of the resource, and make sure that it's ready to use so that you can drop it or execute it as a hidden payload. So let's check another import, and in this import, we'll check the Open Mutex import. So Mutex stands for Mutual Exclusion Object. And for the first call in this specific code segment, this variant will try and open a new mutex. And if the mutex exists, then it means that another copy of the variant is still running in the system. So it will perform a couple of checks. So as you can see over here, and it will use the test variables EAX. And if it returns a handle of EAX is not equal to 0, then it means that the mutex is still running in the system. And so it jumps on another clean code and exists. So this is a feature of a malware variant that is trying to prevent multiple instances of the same variant from executing on the same system. Then this is the sleep delay. So it will sleep for a specific time, possibly as a part of a retry or re-entry into the specific loop. Then it will call back the loop again if the counter hasn't been breached. Then once it's done, it will close the whole handle and continue with the other segment of the code. So this ensures only one active instance runs in this specific system to prevent conflicting file writes when the ransomware is trying to encrypt some of the files in the system. It will also try and prevent excessive CPU and network usage, because as we know, most malware variants require a lot of system resources to execute some of the malicious processes. And it will also prevent any abnormal behavior detection, because as you can imagine, if you have multiple instance processes executing at the same time, then it might look suspicious and the system might start running slow. So this is a preventative measure used by this WannaCry variant to prevent multiple infections.